Lawrence Livermore National Laboratory and its partners rely on timely development and deployment of advanced materials and manufacturing to support a variety of national security missions. Data science plays an essential role in the lab's mission fulfillment, and its Data Science Institute is the laboratory's hub for big machines, big data, and big ideas, and operates at the confluence of high-performance computing, rich scientific data sets, and innovative technologies. Interdisciplinary teams are applying machine learning techniques to remove bottlenecks and speed up the time to deployment in the materials and advanced manufacturing development cycle.
A big problem with manufacturing data, or data in general, is that it's not always collected in a clean fashion. Messy data is a reality, but in order to start thinking and tackling machine learning problems, you have to curate some useful bit of data. There's a number of data streams that we can collect throughout the process, including video data, temperature profile, and other information. And what we're trying to learn from that data is what the end quality of a part is, whether it's a continuous laser track that we've built, or whether it's a particular thickness, or whether layers have fused together appropriately. All of that is important information we can glimpse via machine learning. What we do here in several of our problems is devise really carefully crafted experiments that collect the gems of data that we need to move forward with. So this microencapsulation is a very important, widely used technique that suffers from a lack of automation. The problem is you have someone who has to watch this thing operate for 8-10 hours at a time. And so what we did is had them collect data under normal operation and developed a machine learning algorithm that sorted good from bad microencapsulation events. After training our algorithms, we had a model that could successfully predict the state of the system, and based on the decisions the algorithm made, we could sort good from bad events, eliminating the need for the human in the loop. Another area where we've applied these approaches is nano printing. And the advantage of this technique is you could use it for a large number of materials to print a large number of part designs, but the problem is you need to optimize the process for each given material system. So what we did was collected a comprehensive data set that allowed us to develop machine learning algorithms that could be used to automate this process. After having collected the data set and published on it, we released it so that it's publicly available for the world to use. Another area where we can apply our techniques is towards metal additive manufacturing, in which we're trying to monitor the process to determine whether or not defects are occurring, fix them if possible, and ultimately guide future designs so that there are no mistakes. Laser track welding is a very important process industrially and at the lab, and you can have plenty of things that go wrong in your process. And the goal would be to leverage the data you're collecting during printing to understand whether or not the process is going poorly or not. And in some cases, fix what's happened. After we made a part, we still want to qualify and measure to see we made what we wanted to. So we're also developing machine learning-based approaches to explore the inspection process. Digital twins essentially represent a virtual representation of your system. And why that's beneficial is you can explore different techniques or approaches or explore pitfalls before actually initiating the manufacturing process. While digital twins are an established concept, machine learning is important because it can distill the salient bits of information that are necessary to correct our digital twin predictions and process. A unique approach that the lab is taking towards these problems is leveraging our deep physical understanding of the process and combining that with the latest and greatest machine learning techniques to have scientifically driven models that leverage both empirical data as well as what we know of the process.
Learn more at data-science.llnl.gov.